Okay, so welcome now to part 3 of lecture number 5 on the introduction to relativistic dynamics in Einstein's world. So now we're up to the point where we want a more fundamental understanding of relativistic momentum and energy. Remember, in the first part of this lecture, we considered very simple collisions, special cases of collisions, and required that the description of the collisions be covariant, okay, and found formulas for momentum and relativistic energy. And now we want to rethink those quantities and find more fundamental ways of understanding them. Well, certainly in Newton's world, we think about momentum and as related to position measurements, and we think of energy in a simple way. And so we want to see what we can do here in relativity. In particular, in Newton's world, the momentum is just mass times velocity, and we write it like that. Now, think about that from the perspective of Galilean transformations. So we have momentum is equal to mass. Well, mass is a invariant under boosts under Galilean transformations. And then we have the time rate of change of the position. Well, the time for Galileo is an invariant. It's the same in all frames, right? That's Newtonian's concept of time. And so momentum has the same transformation properties under Galilean boost as x does, or actually the derivative of x. But the transformation properties of momentum inherit the transformation properties of position in such a simple way, because all the quantities here are invariant in Newton's world except for x, and x determines the transformation properties of p. So now we want to think about how can we generalize momentum to Einstein's world. Well, let's take the same philosophy, okay? Okay, so we can write down P is equal to m. That's the rest mass. Rest mass is by definition an invariant, because in Einstein's world, what does rest mass mean? It means you go to the rest frame of the particle and measure the mass. That's an invariant concept, of course. But in Einstein's world, of course, time is not invariant. So that won't do if we're going to have momentum and position have the same transformation laws. So we need a replacement for time, and of course, and what we think of course, is the invariant time, the proper time, as measured in the rest frame of the particle. We write that as delta tau, as we've introduced in previous lectures. Okay, so again, we introduce a time which is an invariant. It's called the invariant time, or the proper time. How do we define it? Well, we go to the rest frame of the particle, okay, and there we have a clock, and we measure time there. Okay, if that's my prescription for the time, then it's by definition invariant. You just because you have to go to that frame and measure it, okay, and so everyone can agree on that. Okay, here tau is the proper time. So so it is Lorentz invariant, as we've discussed when we discussed the geometry of Minkowski diagrams. So in this case, P will transform like x, okay, and I can finally relate my proper time to the time that passes in the lab. Okay, my velocity, my particle is moving at a velocity v relative to the lab. Okay, so a clock at rest in the frame of the particle is observed to move at a velocity v relative to the lab. So a person in the lab measures that time interval d tau to be dilated when he measures it on his clocks at rest in the lab, and so you have that dt is equal to gamma times d tau. D tau is the proper time, the time on a clock attached to the particle. And in this case, I've written it very explicitly, although I'll usually not do that, but just to introduce it, gamma is a function of the velocity, and the velocity is changing. Right? So I go to the instantaneous rest frame of the particle. Look at how clocks are developing in that frame. that defines the proper time, and so that's d tau. And then at that particular instant, I can calculate the velocity. I know the velocity relative to the lab, and I can calculate gamma at that particular time. And so I can calculate the time that passes in the lab for that little interval, okay, in the rest frame of the particle. So dt is gamma times d tau. Okay, and that's the critical observation. Okay. So now I can go back to this formula and see that it works, okay, because P is now m d by d tau of x, but d tau can be replaced by dt over gamma, so gamma ends upstairs and dt downstairs, and I get gamma m, and that's dx by dt, that's the velocity. So you see this formula written in this slick fashion reproduces what I derived before, that P is equal to gamma mv. Okay, and that's the point of the exercise. I'm not really doing anything new. I'm just incorporating what I learned from part 1 of this lecture and writing down the momentum in a more fundamental fashion that incorporates it. Okay. Now I can ask, how does P transform under boosts? It transforms like x. Okay, the position. Okay, I remember the Lorentz transformations, how x transforms. Okay, I know how x goes to x prime, and I know how that x contributes to t prime as well. Okay, x mixes with time under a boost, under a Lorentz transformation from one frame to another. If we had a 4-vector of t, x, y, and z to give me position and time, okay, then I know how that will transform to t prime, x prime, y prime, and z prime. Now in the case at hand, I'm discussing momentum, and so I have again 4 quantities, and I only understand 3 of them: the momentum, px, py, pz, and I've written that down here, and I'm wondering, put a question mark here, what accompanies them in the time slot. You see, because my challenge here is to write down energy and momentum conservation so that it's true in all frames. I've noticed that momentum transforms like x, but when I transform x, I mix in t, okay, to write down a Lorentz transformation. So I have the challenge: what mixes with p under a Lorentz transformation? What is question mark here? Well, look, it's going to mix with something like t, and it's going to have some character of this variety. So it doesn't take a heck of a lot of creativity to try something like, instead of dx d tau, to try dt d tau. Okay, and then I'm going to put in the factors of m and c squared so that I get an energy, something with the correct dimensions to be an energy on the left-hand side. So this is what I'm going to try. It might be wrong, but let's give it a go. In particular, dt d tau, I know what that is. Okay, I just calculated that over here. dt d tau is gamma. So I can get rid of this gamma, okay, which is a nice space-time way of representing energy. And now I can represent it in terms of velocities and gammas. It's gamma. So E is equal to gamma mc squared, and that's of course exactly right. That's the relativistic energy, and that's what I'm shooting for. Okay. So now I have space-time formulas for both the relativistic momentum and the relativistic energy, and it looks like, okay, and I can see now that relativistic momentum and energy are going to transform just like x and t, because all the other ingredients in the formula are Lorentz invariant. Okay, and that's what we point out. That's what we point out here. Okay. So I use the note. So I'm going to introduce some notation here. It's called 4 vectors. Okay, and so I'll write. I'll put an index on x upper mu as being x0, x1, x2, x3, and that's just shorthand for c times time, x coordinate, y coordinate, and z coordinate. So mu will run from 0 to 3, and I just represent my four quantities of time and those three quantities for space as a 4 vector. Okay. Okay. And I know how the 4 vector transforms under boosts. That's what we've done already. That's Lorentz transformations. So now I can read off the transformation laws for the energy and momentum because they follow from the transformation laws of t and x. Okay. Once I identify 4 vectors in any context, okay, they inherit the same transformation properties as x and t, Lorentz transformations. And so it's very convenient for me to find 4 vectors to formulate relativity and to formulate the idea of covariance. Okay, that's the idea that we'll be using again and again to find the systematics in these underlying formulas. Okay, so let's check that out. So let's imagine transforming from one frame to the other, energy and momentum. Okay, so energy in a frame S prime, how is it related to the energy and momentum in the frame S, where the frames S and S prime are related in the usual way, that S prime moves to the right in the frame S with velocity v. So I've written that down. I've written down the formula for E prime in terms of dt prime, okay? And then now I'll steal the Lorentz transformation for T prime, okay, as gamma T minus 1 over V squared, 1 over, minus V over C squared times X, and it's X1 in this notation, the direction along the beam, the X direction, not the transverse directions. Okay, so I see how that E prime is equal to this combination, but then I see here mc squared dt by d tau, that's E in the other frame, and then I see gamma m dx1 dx1 d tau. Okay, I see m times dx1 d tau. That's the velocity. That's the velocity in the x direction in the frame S, and so I got the transformation law for the energy, and similarly for the momentum in the one direction. P1 prime is equal to m x1 prime d tau. I write down the Lorentz transformation for x prime. I've done that here. I identify energy and momentum in these formulas. Okay, gamma m times okay, so gamma, so m times dx d tau, that's the momentum, okay, in the other frame. Sorry for stammering around there. Okay, and then I have that mc squared dt by d tau is the energy. So I pick up this c squared downstairs, and there I have for you the transformation law for the first component of the momentum. The transverse components of the momentum are unchanged by the boost, okay, because the transverse directions, lengths are unchanged by the boost. Okay, so we see in this case that energy, okay, and momentum mix under the boost. Here's energy, but energy is also down here in the formula for P prime. Here's momentum. Oh, but momentum is also here in the equation for E prime. And so just like space and time mixed in Lorentz boost, energy and momentum mix under Lorentz boost as well, because they share the same transformation law. Okay? And so I write the momentum then as a 4 vector, has the same transformation law as x mu. Its zeroth component is E over C, just getting the dimensions right. And then the other 3 components are just P in the x direction, P in the y direction, P in the z direction, which I write as P upper 1, P upper 2, and P upper 3. So we got to get a little used to this notation with indices, and we're going to get good at this as the course goes by. So make a note of it. Now we can start reading off some of the properties of the momentum, because it inherits a lot of its properties from x and t. In particular, we recall that Lorentz transformations have an invariant. Okay, t squared minus x squared is the same in every frame. Well, that's going to now be true for this other 4 vector. Its 0th component squared minus its spatial vector component squared is going to be an invariant. It's going to be m squared c squared. And it'll be the same in all frames, and that's what's written here when I put the primes on it. Okay? And so I simply do the calculation. I actually have done this one already in the course, and I verify it, again, that e squared over c squared minus the vector p squared is equal to an invariant. It's m squared c squared, and that gives me my answer. Earlier on in the course, I identified this as the energy-momentum relationship for a particle, that E squared is equal to P squared times C squared plus M squared times C to the 4th. And it follows from this perspective as being a basic invariant of the 4 vector. The 4 vector has the same invariant structure that x mu had, space and time, because of our formula to make energy and momentum out of derivatives of space and time. Okay. One of the interesting things here is that we notice that even if a particle is massless in relativity, so m goes to 0, it still carries energy and momentum. Okay, we get that E is equal to PC, taking rid of the square roots, so E is equal to PC. We've used this formula before, now we see it again from a fundamental perspective, and I'm going to tell you that we'll derive later that it applies to light, and it also applies to gravity waves. These are waves which travel at the speed limit, and they carry both energy and momentum. We've seen that for light from several perspectives already, from our little box and from our other examples. Okay, so let's discuss. So we've introduced the idea of 4 vectors. Let's write down some notation just to get used to it again. We'll be talking about 4 vectors and tensors. We'll have lots of 4 vectors, and I'll notate them as A with an upper index mu running from 0 to 3. They'll, by definition, transform like x mu under boosts. So I know how they transform. They'll have a quadratic invariant. I'll write that as A squared, as A dot A, and it's going to be the 0th component squared minus the spatial component squared. I'm just stealing this, of course, from the way x transformed. And of course it's going to have that structure just because that structure is guaranteed by the property of the 4 vector under boosts. Okay, and then there's lots of examples of 4 vectors and lots of examples of inner products. For example, I can take 2 4 vectors and take their inner product, which I call A dot B, and I just define that as in this way, just a generalization of the length, okay, as A naught, B naught minus AX, BX, etc. Again, since both of these quantities A and B transform the same way as X and T, it's guaranteed that this dot product being invariant under boosts. We're going to find that very handy in developing the conceptual basis for relativity. Okay, I give some examples here, like that. Okay, and so you can take a look at those examples. We'll be returning to other examples as we move on with the course. Now we can go back again, developing formalism to look back at Minkowski space and the metric of Minkowski space, which we introduced before. Remember, we had the invariant interval as delta S squared is equal to C squared delta T squared minus delta X squared minus delta Y squared minus delta Z squared. And that interval we showed was invariant, as I indicated on the previous sheet. But now we think of that as we think of this as the distance in Minkowski space between 2 events which occur infinitesimally close to one another. That's why I've written differentials as opposed to delta X's and delta T's. Okay. So that tells us the invariant distance in Minkowski space, so naturally we call that a metric. And I use this notation G mu nu. Okay, it looks like excessive notation, but let me tell you, it's going to be important in general relativity, and that's where we're headed. So let's write down the notation now. The notation for special relativity will be a very simple special case of all this, but we'll get used to the notation in this way. So I write ds squared as the double sum over the indexes mu and nu of g mu nu times dx upper mu and dx upper nu like that. Okay, okay. And in this case, it reduces down to this. This is just excessive notation, okay? But Minkowski space in Cartesian coordinates we know as G0, 0, 1, that corresponds to 1 over here. And then the other components, G11, G22, G33 are minus 1. That corresponds to the minus signs in the spatial bits of the invariant interval, and the others are 0. So this big double sum just reduces down to this, because the only non-zero components of the metric are those. But it's a metric. You can choose different types of coordinate systems. You don't need Cartesian coordinate systems. And so I've written it down in the case of spherical coordinates for R, okay? And then I've written down what G is in spherical coordinates there, and then I can write my metric in that form as well. Okay. So there are examples like that in the text, and I encourage you to look at that. Okay. Now in taking these inner products and such, it's very convenient to have a notation which incorporates the metric. And to do that, we introduce the idea of contravariant four vectors with upper indices, and covariant four vectors with lower indices. Okay? And they're really just a statement of one another because they're related by this process. That is, to make a lower index 4 vector, I take the upper index 4 vector and multiply them by the metric as shown there, contracting or summing over the index, the lower second index on the metric and the upper index on the. Okay, in the case that we're doing with Cartesian coordinates and special relativity, this is really simple because most of the components of G are either 1 or minus 1 or 0, and so you see that A upper 0 is A lower 0, A upper 1 is minus A lower 1, etc. Okay, but you see, the payoff is that now I can go back to my inner product, which is written here, and rewrite it with upper and lower indices with no signs and no G mu nu's at all, right? You just verify that by inspection, okay? Just by this rule of the pluses and minuses. And then I've written here, for example, p squared again as p dot p. I'm writing it now as contravariant p, covariant p, and then I just sum off the four terms. That generates the minus sign here in the interval, and I get my invariant. Okay. So this is going to prove to be useful notation, and there's plenty of examples worked out in the text, and I encourage you to do that. Other things we do is that we like to write boost in matrix form. Okay, so we're doing boost in the x direction, and I can write the Lorentz transformation in a matrix form. So I write as a matrix a little vector t prime and x prime as a vertical column here. Then I have a 2 by 2 matrix which brings in the elements of the Lorentz transformation, and then I have my vector in the frame S. So here's the vector Tx in the frame S. Here's the boost, and I get my vector in the frame S prime. Okay. Now I can write that in a notation with indices showing, as shown here, that x prime upper mu is equal to just a matrix times x. And I'm writing the matrix like this, keeping upper and lower indices assigned like that. And then I can read off from this formula what the L mu nu, that matrix that is the Lorentz matrix that characterizes the boost as gamma minus v over c gamma, just reading off just reading off here, and reading off here and here what they are. Okay. Okay, and so this particular expression here with the matrix written out from the Lorentz boost formula is how four vectors transform from one frame to another, and that might be for the momentum energy four vector, the space-time four vector, and other ones that will meet along the way. So they'll all have the same common transformation property, and we'll study it. Now, in some cases, I'm going to, in addition to having four vectors, I might have the product of components of a four vector, like A prime, B prime, with a mu here that might be between 0 and 3, and a nu here that might be between 0 and 3. A quantity like that transforms as well, and just using this formula, you know, for how the four vectors transform, I see how the product of the two components of the four vector transform. It transforms like that. Okay, this transformation law will also be important. It's the transformation law of tensors. It's called a second rank tensor, and we'll be studying it as we progress through the course. Okay. So let's stop here, and then pick up more formalism next time. So take a look at your notes. Take a look at the textbook. I know we're covering a lot of new formalism now. It's a lot to digest. So give it a shot. In recitation section, we'll be doing a lot of examples, okay, and a lot of problems on this subject, and we'll continue here discussing transformation laws more thoroughly in the next part of this lecture.